Okay. Can you hear me? Okay. Okay, thank you for this opportunity, Franco. My name is Lorenzo Chicchi. I'm a PhD student here in Florence at the Department of Physics. And today I would like to talk about one of our last work, a work that falls in the field of artificial neural networks. And in particular, in this work, we presented a new model of artificial neural network called recurrent spectral networks. So let me start with some reasons behind this project. As the name suggests, neural networks are in some way inspired by the biology. But we all know that the gap between artificial neural networks and natural neural networks is very, very huge. And as a research group, we think that implementing some aspect from the biology can be very useful to develop new model of artificial neural networks. Okay, and in this sense, our model is just a first and small step in that direction. So if this is the distance between artificial neural network and natural neural network, our model will be more or less here. So very, very close to the side of artificial neural network. Okay, my talk will be in the first part a bit introductive because I think it's necessary to introduce artificial neural network for those of you unfamiliar with these tools. So let me start with this brief introduction. A neural network is a mathematical model by which we can approximate very complex function targets. As the name suggests, we can represent these models with by means of a network, and this is the most common architecture called feed-forward architecture. And in this kind of architecture, the nodes are organized in different layers. So we have a first layer called input layer, where the input of the function we want to approximate enter, and then the signal is propagated inside the network by following this very simple rule. So we have a linear transformation described by this sum and by these weights, and the application of a nonlinear function. And these weights, W's, are also the trainable parameters of this model. Okay? So what is the idea? Typically, we have a data set, so an ensemble of examples input target. We can take one input, for example, in this case, we have an image. We can transform it in a vector, and we can put the vector inside the neural network so that we have an output from the neural network. And when we say that we train a neural network, what we actually do is to minimize a loss function, that can be very different, but in general is something proportional to the difference between the target we would like to have and the output that we read in the output layer. Okay? So, but from a mathematical point of view, a neural network is very simple because every layer transfer is just an application of a non-linear transformation described by a matrix that in general is a rectangular matrix, and the application of a nonlinear function. Okay? So this is a very brief introduction to neural network. So now we can introduce the two main ingredients for our model. The first ingredient is the deep learning spectral domain. Recently, some of my colleagues have introduced a new formulation for the feed-forward architecture. And in particular, they introduce a new way of describing the linear transformation in the layer transfer by describe it not with a single matrix, but with a spectral decomposition. So the linear transfer is described by these products. So what does it change? Now we have another set of trainable parameters that are not anymore the weights W, but the eigenvalues and the eigenvectors of this decomposition. This brings to very interesting things. This is not the focus of this talk, but if you are interested in this part, you can ask me during the lunch, or you can also ask Lorenzo Giambagli that is here. Okay. The second main ingredient for the recurrent spectral networks, as the name suggests, are the recurrent neural networks. So if you search on Google recurrent neural networks, you will find a lot of different subclasses of recurrent neural networks, the LSTM and so on. Most of them are very engineered, but we are interested in the most simple case, the very simple case. That is the one here represented. These are simple recurrent neural network can be seen in two different ways. The first way is to see it as a completely fully connected network where the input enter and we just iterate this network. So we apply the adjacent matrix, the weighted adjacent matrix of this network, and a nonlinear function. So in a certain way, this is equal to have a feed-forward neural network, as the math suggests, with exactly the same matrix in each layer. So now we don't have layers, we have iterations. And what is important is that this matrix is a square matrix and is the weighted adjacent matrix of this network. Okay, so with these two ingredients, we can introduce our model called a recurrent spectral network. This is the logo. I like it. And the first thing we do is to not to decompose, but to describe the weighted adjacent matrix W of a recurrent neural network, of a simple recurrent neural network with this spectral decomposition. So with these products. And moreover, we introduce some constraints in this decomposition. First of all, we fixed to 1 some of the eigenvalues. So they are not trainable. They are fixed to 1. And we also fixed the relative eigenvectors. We can call them recognition eigenvectors. While the other eigenvalues are bounded to have a magnitude value lower than 1. Okay, so the new set of trainable parameters are the bounded eigenvalues and the relative eigenvectors. Well, if the dynamics of this network will be linear, you easily understand that after enough iterations, all the dynamics will collapse in the subspace defined by these eigenvectors, because these eigenvalues are bounded to be lower than 1, so they vanish iterations by iteration. Okay, but the dynamics is not linear a priori, and so we introduce a non-linearity that vanish in time. Okay, so after enough iteration, we actually have a dynamics that becomes linear, and we can make assumption on these on the dynamics by looking at the spectral decomposition. Okay, so regardless of the values of the trainable parameters, as I just said, the final state will be a linear combination of the recognition eigenvectors, the 5R. And these eigenvectors can be fixed a priori, or they can be also included in the trainable parameter, so that the network learn what is the better final space. And so we can define a classification task by asking the network to learn how associate each class of the problem to one specific final state. And in particular, we consider the simplest case where we have C classes in the problem and the same number of final eigenvectors, so that we can simply ask the network to associate each class of the problem to a specific eigenvectors and not to a linear combination. This just help to write the loss function. This is more or less the loss function. So we simply ask that after enough iterations, or better, after a number of iterations fixed during the train procedure, the final state, once decomposed on the base 5, has to have all 0 coefficients, but for the one associated to the class of the input. So we want the final state will be one of the eigenvectors. Okay, this is what we obtain by working with the very well-known MNIST dataset. Is a dataset of handwritten digits. We can also define an initial linear transformation defined by this blue network. This is just to have the possibility to work with the recurrent spectral networks with the size different from the input size. But in this particular case, we use a recurrent spectral network with the same size of the input, so that we can represent the network with an image of the same size of the input, so that each pixel is corresponds to one neuron of the recurrent spectral network. And also, just to help the visualization, we use as recognition eigenvectors some vectors that can be reshaped in order to manifest as a stylized version of the number to be classified. This is just to help the visualization. And as you can see, starting from 2 different initial conditions on the network, the dynamics evolves and reach the 2 corresponding eigenvectors. So what are the properties of these models? Of this model. So the first property is that the recurrent spectral network is able to, in a certain way, keep memory of the classification. So suppose to have 2 networks. One is a recurrent spectral network, and the other one is a simple recurrent neural network. And as I said before, during the train procedure, we define a number of iterations after which we compute the loss. Okay? If we use a recurrent neural network, a trained recurrent neural network standard, we have an high accuracy of this network only when the number of iterations during the evaluation process matches the number of iterations used during the train procedure. While with a recurrent spectral network, we see that the accuracy grows during the first iteration, also before the number of iterations used during the train. And when it reaches a maximum values, these values is maintained also after the number of iterations used during the train procedure. So if you have a black box that is a recurrent spectral network, and another black box that is a standard recurrent neural network, with the second one, you have to know the exact number of iterations you have to make. While with a recurrent spectral network, you simply have to wait enough and let the dynamics converge, and you will have a right answer with this accuracy. Okay? The second problems we tried to face using the recurrent spectral network is the problem of sequential learning. What is the problem of sequential learning? Suppose to have two different data sets, and you want to use a neural network to learn the first data set, and then you want to learn the second data set with the same exactly neural network without forget the first data set. Okay, this is the sequential learning. And we tried to face this problem. First of all, we defined two data sets. For sake of simplicity, we used a partition of the MNIST data set so that the first 5 digits are in the first data set and the second, and in the others in the second data set. And then, first of all, we introduce a sort of quasi-orthogonality in the matrix phi. And we do it by introducing this parameter, epsilon, that if it is equal to 0, this, in the direct space, we have two completely separated networks, and this is not so interesting. But if epsilon is close to 0, what we have in the direct space is a completely fully connected network, while in the reciprocal space, we have this sort of two family of eigenvectors, where since every columns of the first alpha of this matrix, so the first alpha of eigenvectors are in a certain way quasi-orthogonal to every columns of the second alpha. So we have this sort of quasi-orthogonality in the space of the eigenvectors. Then we arrange the eigenvalues in this way. So we have the first 5 untrainable and fixed one eigenvalue in the first positions. Then we have a first set of trainable eigenvalues. Then again, the second set of not trainable and fixed eigenvalues, and then the second set of trainable eigenvalues. So our strategy is the following. We start to train the network on the first data set, and during this phase, we acting on the first set of trainable eigenvalues and on their relative eigenvectors. And during this phase, what we do is to turn off the second part of fixed eigenvalues. In some way, we are saying to the network that the second part of the memory is not accessible, and all the dynamics have to converge to the first subspace of the final subspace, the one defined by the first 5 eigenvectors. Then we do exactly the same things for the second data set. So we turn off the first part of the memory, let me call in this way, and we turn on the second part, while we act for the training on the second set of trainable eigenvalues and on the relative eigenvectors. And at the end, we turn on all the once eigenvalues, so that when the network is completely trained on the 2 data sets, we let all the memory accessible, okay? So what we do in a certain way is to force the network to store the information from the first data set in a part of the memory that is in some way quasi-orthogonal to the other part of the memory. Okay, we store the information of the 2 data sets in a sort of quasi-orthogonal subspace. Okay, what we obtain is represented. So in these 2 peaks in the x-axis of these 2 images, there are the epochs that are the training steps. If you don't know, okay, I just finished. And during the first 100 epochs, we train the networks on the first data set, while during the second 100 epochs, we train the network on the second data set. This is what we typically obtain with a standard recurrent neural network, but also with a feed-forward neural network. It's just to show what typically we have. And as you can see, when we start to train the network on the second data set, the accuracy on the second data set increases very quickly, but the accuracy on the first data set goes immediately to 0. And this is what is called catastrophic forgetting. This is very typical in neural networks. While with our strategy, what we have is that when we start to train the network on the second data set, we have a little drop in the accuracy on the first data set, while the accuracy on the second data set grows until more or less they have the same, they reach the same values. Even if it's not the maximum values, I think is an important step in the direction of obtaining a sequential learning. Okay, let me make just 2 conclusions. So, as I said, I think it could be important, not only us, but we as a research group and we other research group, we all think that it can be important to reduce the gap between, or better, to implement some aspect from the biology in the artificial neural networks, and also aspect from network theory, so eigenvalues, spectral decomposition, and so on. And in particular, the spectral formulation of deep neural network can bring to very new models. For example, the one I've shown today, the recurrent spectral networks, that seems to show some properties that can be obtained by simply work in the direct space. And if we want more binary-inspired models, we have to introduce the dynamics also in the evaluation process. And this is what we try to do with this model. So let me thank the other authors, Lucio Fanelli, Lorenzo Giambagli, Lorenzo Buffoni, and Timoteo Carletti. Thank you.
Thank you. And so, as usual, there are questions, comments, please.
Nice talk, nice idea. I would like 2 comments about this. One is how much the behavior, the remembering of the network depends on the vanishing nonlinear function, which is how much is, and the other one is the, if you studied the generalization properties and compare between the 2 types of networks.
Okay, so first of all, the things about the keeping memory. Obviously, there is it is important that this number of iteration, the number of iteration used during the train, is in some way connected to these parameters alpha here. Okay, so you can fix one and the other. Okay, there is a connection between these parameters. Okay, so simply you have you need to have a linear dynamics after k star iteration, and you can fix the alpha parameters in order to have it. Okay, we don't have any constraint for the moment. Okay, and for the generalization, I mean, we are very interested in studying generalization problem because we don't know more or less anything about it, but we just see that these models have more or less the same generalization capacity as the standard fit for a neural network, but probably if we are interested in study this kind of problem, we have to face more complex data set. In a certain way, MNIST is too much easy to make an assumption, because more or less every model generalize very well on
because you can train on a set of number and then test on another set of numbers.
Yes. So it's very interesting. Thank you.
Okay, thanks. I don't know if maybe also the next speaker has some question. Let me try. Just wait a minute. What is it? Okay, now. No, now you cannot hear us. No, there is something that makes some noise.
Yes, I was. Yes, wanted to congratulate the expositor. It was a very nice talk. My only comment.
Try with the headset, earphones. Yes, but in this, like, we don't hear you in this way. So clearly the noise is off, but can you hear us? No? Arturo? We don't hear you.
Hello, you can hear me? Excuse me?
Yes, this time it seems to work.
Sorry, I have some technical problems, Franco. Maybe yes, let me try to fix them.
Entendido. Bluetooth.
The last thing that you did was not really working. Vabbè, penso che forse no. It seems that there's something that makes an interference. I have Bluetooth as the last word, so maybe there is something like this that is okay. Now it seems no. No, we only hear noise. Try to switch off all the devices. Yes. Che cazzo? Oh. Okay, but we hear a lot of noise. To speak. I cannot hear you very well. Mm, 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 mm. Can you try to speak? Can you hear me now?
Yes, I hear you, Franco. You can hear
Yes,
me?
but we hear a lot of noise.
A lot of noise. Let me try to fix that. Give me a second.
Don't you have some We still hear a lot of noise. Try to speak, Arturo.
Hello, can you hear me now?
Okay, now you can present. Okay, thanks.
Oh, sorry about these difficulties, but now you can hear me, okay? And you can see my talk also.
Okay, go on.
Okay, thank you, and sorry, and thank you very much for the invitation to the conference. I apologize to be unable to be in person, but anyway, I'm quite grateful to be at this very nice conference and quite high-level talks that have been presented so far. So the contribution that I want to present to you is a kind of showcase about some of the ideas that myself and collaborators have been working recently in the intersection between machine learning, statistical mechanics, and discrete stochastic processes that we believe share a commonality between this kind of subjects that can be useful, can be used in integrated fashion to understand some of the more pressing questions regarding machine learning. For instance, the questions regarding complex structures, complex temporal structures in sequential data, emergent properties, and to try to understand the emergence of properties by machine learning algorithms and so on. So I will start with well, this is an overview of the talk that I will present to you today. Some practical examples that are in which the problems that we try to solve are inspired. The problems that we're trying to solve with these techniques. Try to give you some practical motivation of that. Some general ideas and people involved with those, and the work in progress in which we are trying to take into account all these ideas and put it together. Okay, so the examples that we are currently trying to understand, the examples in which we are currently working on, regard the streaming of streams of bits, streaming of data samples given by streams of bits that we can find in a number of applications, and we're also interested in the kind of data that has temporal structure, that has complex temporal structure. For instance, found in discrete time series, and here there are a number of examples. We have this economic. We can observe this kind of data, for instance, in economic time series and in time series found in ecology and renewable energies and so on, and different applications. We can also find this kind of data in a technique named thresholding. This thresholding technique refers to the selection of a particular threshold above which the data is believed to have some other particular meaning or to have some other qualitative importance. So it's interesting to make a distinction between the data below the threshold or above the threshold. And as we can see here, we find different regimes in this kind of data. For instance, we may find we can find data that has large gaps between the appearances of important or of interesting features. We can find data that's very sparse. We can find also sequence of data that are quite packed together and so on. So we have a number of different temporal structures, different sequential structures that are characterized by different correlation and dependency measures. So this kind of sometimes dispersed, sometimes compact sequence of bits, sometimes with the presence of a number of different kinds of temporal dependencies among them, makes difficult to find a correct sample size in order to learn the patterns and this kind of data, or to model the data by classical stochastic processes. For instance, if you model this by a discrete dependency process, like a Markov chain, maybe if you have very sparse data, maybe you will need a very large matrix, transition matrix sizes in order to make the modeling, which at the end involves an exponentially large number of parameters in this kind of data. And other applications in which we can observe data of this type is in natural language and another type of coarse-grained time series that are coarse-grained microscopic or aggregates from binary data. For instance, and this is an example taken from an article from 2005, in which the statistical dependencies between coarse-grained patches of a text, of a literary text, have been observed. And once the dependency structure of that kind of patches of written text have been studied, they have found that the statistics followed by the sequential patterns obey some anomalous diffusion behavior. They behave like anomalous diffusive process. There are a number of other kind of applications in which this type of behaviors in sequential data have been found. So the first idea that I will try to expose very rapidly here regards a simple model that tries to capture this kind of anomalous diffusive behaviors that has transitions between the different regimes of different, let's say, from normal to anomalous diffusion. And we have been wondering for a number of years now, a colleague of mine, Hernán Larralde from UNAM, and myself, we have been trying to wonder in which sense we can find the simplest model, let's say, the simplest model capable to capture this kind of transitions between normal and anomalous diffusion. So the first step that we have taken a number of years ago was to propose a single delay. Let's think of like a Markovian process, in which instead to have the dependency among single time steps, think about it like dependencies between a period t in the past that makes the influence of the step t steps further away. So by that simple single delay model, we had been able to reproduce some of the transitions between normal and anomalous diffusion. But now we are putting forward a little more generalized model in which we have two delays, in the sense that the bit or the step at each time depends on two previous steps. First step at the time capital T A, and the other step at capital T B times before. So it turns out that depending on the ratio between these two periods, stochastic periods, let's say, or maybe delays, stochastic delays, we can observe a very different behaviors on the time series. And here we have an example in which we have these dependency parameters, all the same parameters. The only difference between the two samples is that we have the second, the most large period, the most past period in the past. We have an integral ratio between the larger period and the shorter period. And in the second example, that we have almost the same difference between the both delays, but just they are not given by an integral ratio between the two. So that just because that non-integral relationship between the second example and the first example, we have a quite different statistical properties between the two, and that can be measured in the coarse grain description. If we construct the random walk associated with the microscopic process, we can see a number of different regimes just because the two the relationship between the ratio between the two delays. For instance, here we have starting with the initial density of 1/2. That is, we have a 1/2 probability to have a bit 1 in the initial sequence, the starting sequence, and it is evident the long range memory effects by observing the variance, and the variance as seen in time it evidently goes to or displays transitions between normal and anomalous, normal, superdiffusive, and subdiffusive regimes. And these transitions are very different regarding the ratio between these two delays. So the point is that with only two quantities, with only two delays, we can, and kind of generalized Markov dependency, we are able to construct a stochastic sequential processes that mimic some of the features found in some complex phenomena like written language, natural language, and some other interesting aspects that are of interest in the learning, are of interest for the learning in learning algorithms and machine learning algorithms are of current interest to be described by this kind of machine learning mechanisms. So this model can be valuable at least to give a playground, a controlled playground to develop machine learning strategies that attempt to generalize from sequential data of this type. So this is the explanation of the phenomenon of this kind of transition between very different statistical features depending on the ratio between these two delays. The explanation is that with a single delay or with a delay, with a pair of delays that are related by an integer by an integer number of by an integral ratio, sorry, between them, you can arrange the data in a fashion that you arrive at a sum of independent persistent random walks. So you have let's say a simple, more or less simple structure made by independent random processes. But if you have a non-integral relationship between the two delays, you cannot make this construction. This construction is broken, and you have a much more complex state. So this is reminiscent of the kind of commensurate incommensurate transitions that you can find, that have been found in nonlinear dynamics, nonlinear dynamic processes. So as I already told you, this kind of controlled model, this model can be used like a controlled playground to train new machine learning algorithms. So another idea that I want to showcase to you today is our work in new machine learning algorithms like this maximum entropy Boltzmann machine that is modeled put forward that has been recently, we are trying to put forward, Franco and I. And the point is that this model leads to a very natural way to, a very transparent way to relate the sample size in the data with the complexity of the learning machine. The parameters are clearly related in this model. So the idea is if we make experiments in which the sample size is important because maybe we have non-stationary data, so it's not the best to use all the available data to train the model, but just to look at patches that are the correct patches to capture some regime of the data. And because this model is very clearly connected to the parameters of the learning model, maybe a natural application of this kind of model is to study this sequential data that is important, as you know, for applications that are currently of current interest, like this natural language processing and so on. But anyway, this is in the simplest version. This Boltzmann machine model reproduces some basic computational aspects. For instance, here we have this learning machine is in connection with the previous talk, is also a neural network inspired in the biological neural nets. The difference with regard to the more traditional artificial neural networks is that we can have loops. We can have loop connections. For instance, we are representing here the preservation or transmission of a single bit. So this kind of Boltzmann machine makes the information processing in a stochastic way, just like biological neurons. This kind of Boltzmann machine artificial neurons fluctuate, and the idea is that the fluctuations are close to the training attempt to give fluctuations in the outputs or on the units that in a statistical sense are correct. For instance, this is an example in which we are trying to preserve a single bit. For instance, if we want to preserve a bit 0 and transmit it, from neuron 0 to neuron 1, let's say that the input neuron is 0. This Boltzmann machine fluctuates with a temperature, and these fluctuations are modulated by a kind of resting voltage. So depending on the interplay of both these parameters, we can control the fluctuations. And the idea in a correct training setup is that in a statistical sense, the 0 bit or the 1 bit is preserved. So we have been working on this. We have a formal model, and we have been working on the construction of basic logic gates by this kind of model. But the idea now is to scale up the algorithm to real-world data in order to perform real-world machine learning, real-world interesting machine learning processing. So the work in progress that I have with my PhD students back here in Mexico is to try to use the fact that this Boltzmann machine depends on quantities related to this, the parameters of the machine, like these voltages and temperatures and so on, and also depends on the topology of the network, the topology that involves all this connection and closed loops and so on, and it also depends on the data. So we have a series of inequalities that must mimic the given data, and this sample size in the data is by these inequalities and by this formula that represents the posterior distribution of the connections in the net, of the topologies in the net, we can make a link between the sample size, the topology, and the network parameters, such that we have a quantity that can be interpreted like a potential for the actual connections between the network, and we can define also stochastic processes that must adapt to the data, but that will be being mimicked by the network. So this is our current work, the current strategy by which we are trying to scale up this Boltzmann machine setup, this Boltzmann machine paradigm, is to try to put this playground of sequential data. There is, we believe, an interesting problem regarding binary data sets. We believe that this Boltzmann machine is, at first instance, oriented to binary data. So maybe an interesting problem regarding binary data is this sequential case. So by the use of this Ornstein-Uhlenbeck process for the actual topologies in the net, as we can see in this formula, we have the sample, we have the parameters of the network and the connection of the network, all related together in a simple updating formula for the topology of the learning machine. So our hope is to given a topology, an initial topology, and feeding that topology with chunks of sequential data, and also taking advantage from the fact that we know that the learning model adapts to an Ornstein-Uhlenbeck process in which we have fluctuations around given a minimum. If the data is adequate for the topology of the learning machine, we should expect that the oscillations or fluctuation of this Ornstein-Uhlenbeck process will be around some minimum. So by this interplace by the knowledge of this of all these features, we expect to arrive to a good model, in the sense that will be good to make generalizations in regard to maybe non-stationary data with difficult structures to be detected beforehand. So we expect to arrive to an algorithm capable to perform good generalization in learning problems on sequential binary data. And that's it. That's the ideas that we are currently exploring. So I hope to have given to you an overview of the kind of work that we are trying to do, that we're trying to put together. And thank you again for the invitation to this very nice and very, very pleasant workshop. I know if you have some questions, I will be pleased to try to answer them.
Okay, thank you. Can you hear me, Arturos? Yes.
More or less, yes. More or less, I can hear you.
Okay, so thank you for your contribution. I ask if someone here has questions or comments. Clearly, we are all still engaged in trying to understand all this stuff, because it is a bit different from what we have heard in these days. But anyhow, I wonder if this approach based on random walks
Yeah.
can be understood as a kind of path integral approach to the processing of data.
I didn't understand the last part, Franco. So sorry. Can you repeat?
Sorry. you are the difficulty here. You are thinking about using random walk to explore data.
Yeah.
Is it something that has some relationship with a kind of path integral approach? Because we were discussing just yesterday about this.
Okay, with the path integral. Well, I must confess I'm not so acquainted with this path integral approach. But
okay, I think it is better to discuss when we have, say, better connection.
Yeah, it's a difficult subject. But
okay, so if you see, Arturo is probably is coming this year, so we have occasion for discussing with him. So thanks, Arturo, again.
Thank you, and I
Bye
hope
bye.
to give you a talk further time in the year.
Okay, don't worry. Bye bye. And
Bye.
so we now have our lunch and be back in 1 hour because I'm time to shrinking everything.